All right, let's talk about one of the most classic showdowns in all of computer science, merge sort versus quicksort. You've got two absolute titans of sorting, and today we're going to put them in the ring. We'll break down exactly how they work, where they shine, and by the end, you'll know exactly which one is the right tool for your job. Let's dive in.
I mean, seriously, have you ever thought about it? You tell your phone to sort thousands, maybe even millions of photos, and bam, it's done. That's not magic, you know? That incredible speed is all thanks to some seriously clever sorting algorithms. And the core strategy behind that power, well, that's what we're about to unpack.
You see, at the heart of both of our contenders today is this one really powerful idea: divide and conquer. Instead of trying to wrestle with some huge, messy problem all at once, this strategy just breaks it down. You split it into smaller, much easier problems, solve those little pieces, and then stitch the solutions back together. It's an amazing trick that turns a slow, painful task into something incredibly fast.
And the playbook for this is always the same 3 steps. It's super simple. First, you just divide the problem, again and again, until the pieces are laughably small. Second, you conquer those tiny pieces, and often they're so simple they basically solve themselves. And finally, you combine those simple solutions back together to solve that original big headache of a problem.
So first up in the ring, let's meet merge sort. I want you to think of this one as the meticulous, super reliable planner. It was developed way back in 1945 by the absolute legend John von Neumann, so yeah, it's a true classic, one of the most dependable sorting algorithms ever invented. Merge sort's strategy is beautifully simple and consistent. It just takes a list and splits it right down the middle. And then it does it again and again and again until every single item is sitting in its own tiny little list. And here's the thing, a list with only one item is, by definition, already sorted. The real work, the real magic, happens in that last step, meticulously merging those tiny sorted lists back together into one final, perfectly ordered array.
And that merge operation, that is the beating heart of this entire algorithm. Just imagine you have 2 decks of sorted cards. The process is simple. You just look at the top card of each deck, pick the smaller one, and place it in a new growing pile. You just repeat that over and over until you've built one single bigger sorted pile from the 2 smaller ones. That's it. So what's its superpower? Predictability, a rock-solid guarantee. With merge sort, it doesn't matter if your data is already perfectly sorted or if it's a complete and total chaotic mess. It will always finish the job in what we call O(n) log n time. And trust me, for big data sets, that's not just fast, it's a promise. It's something you can absolutely count on. But, you know, every hero has a weakness. Merge sort's kryptonite is memory. To do all that careful merging, it has to create a whole new temporary array that's the exact same size as the original one. So think about that. If you're sorting a gigabyte of data, you need another gigabyte of RAM just sitting there, free. In situations where memory is tight, that's a pretty big deal.
Okay, now for our second contender, quicksort. If merge sort is the planner, quicksort is the high-risk, high-reward speedster. Developed by Tony Hoare in 1959, this is often the go-to algorithm for general-purpose sorting because, well, on average, it is just wicked fast.
Now, the whole game for quicksort revolves around one central idea, the pivot. The algorithm just picks one element from the list, any element, and calls it the pivot. Then its entire job becomes shuffling the list around so that all the items smaller than the pivot end up on one side and all the items larger than the pivot end up on the other. That choice of a pivot is absolutely everything.
So quicksort strategy is almost the reverse of merge sorts. Remember how merge sort did all its work at the end in the combine phase? Well, quicksort does all the heavy lifting right up front. It picks a pivot, it partitions the entire array around it, and then it just recursively calls itself on the 2 smaller sections. The combine step at the end is basically free because, hey, the sorting has already happened.
And its superpower? Just sheer, blazing practical speed. On average, it runs just as fast as merge sort, O of n log n, but in the real world, it's often faster. Why? Because it sorts in place, meaning it works directly on the original data without creating a copy. This is huge because it means the data it's shuffling around can stay in the CPU's fastest memory, the cache. This gives quicksort a pretty significant real-world speed boost.
But, and this is a big but, here's the high-risk part.
If you get really unlucky and consistently pick bad pivots, like, say, always picking the smallest or the largest element, the partitions get completely lopsided. And when that happens, Quicksort's performance just falls off a cliff. It degrades to O of n squared time, which is catastrophically slow. So its amazing speed, it's not a guarantee, it's just a very, very high probability.
All right, we've met the planner and we've met the speedster. Now it's time for the main event. Let's put them side by side and really see how they stack up.
Okay, this table lays it all out pretty clearly. Their average time? Identical. But just look at that worst case time. That's a massive difference. And for space, you can see Merge Sort needs that big chunk of extra memory, O of n, while Quicksort just needs a tiny bit on average. And then we've got these two other critical things, stability and whether it's in place. Let's break those down.
So when it comes to speed, the trade-off really boils down to this. Do you want a performance guarantee, or are you willing to gamble for a shot at higher practical speed? MergeSort is your reliable workhorse. It's never going to let you down. Quicksort is the race car. It's probably going to win, but there's that small but very real risk of a spectacular crash.
Their memory usage is also just fundamentally different. MergeSort goes and asks for a big, separate block of memory for its temporary array. Quicksort, though, it's clever. It uses the program's internal to-do list, what's called the call stack, to keep track of its work. Normally, this is super efficient and small, but in that dreaded worst-case scenario, that to-do list can get so long that it overflows, which can crash your whole program.
Now for a really critical distinction, stability. A stable sort is one that promises to keep the original order of items that have equal values. So imagine you're sorting a spreadsheet, first by city and then by name. A stable sort on name won't mess up your original city groupings. MergeSort is stable by its very design. Quicksort, with all its long-distance swapping, nope, it's unstable. And for some applications, that can be an absolute deal-breaker.
So after all that, who wins? Which one do you choose? Well, the truth is, there is no single best algorithm. The real champion depends entirely on the specific problem that you're trying to solve.
You're going to pick MergeSort when stability is a must-have, or when a worst-case slowdown is completely unacceptable, like in a real-time system. It's also the clear winner for things like linked lists, where you can't just jump around in memory, and for sorting datasets so massive they don't even fit in RAM.
On the other hand, you're going to reach for Quicksort most of the time you're sorting arrays that fit in memory, and your number one goal is average case speed. If you're short on space and you really don't care about the original order of equal items, Quicksort's low memory use and awesome cache performance often make it the faster choice in the wild. But here's the real secret from the pros. The best solution isn't about picking one over the other. It's about combining them. Modern production-level sorting libraries all use hybrid approaches. Take Python's TimSort, for example. It uses MergeSort's overall strategy to get that guaranteed performance and stability, but for the small, broken-down pieces, it switches to a different algorithm that's way faster on tiny lists. It literally gets the best of both worlds.
And you know, this whole showdown teaches us a really crucial lesson that goes way beyond code. It's not about finding the single best solution for everything. It's about understanding the trade-offs and picking the right tool for the job at hand. So the next time you've got a complex problem, ask yourself, do you need a rock-solid guarantee or are you willing to bet on raw speed? Thanks for tuning in.